So I'm going to re-record it. It's not a big deal. Except it's going to take 5,000 years to decide to start recording. Come on. It's just spinning, spinning, spinning. Did this in first period too. Yeah, the broadband, the whatever, it's, there it goes. It's really struggling today. All right, so I've mentioned the Coriolis effects. We're going to be talking about it specifically today. I will show you one physics equation with it, but we're not going to use it to calculate anything. This has a lot of very upper level physics in it. And so we are going to talk specifically about the Coriolis effect. This entire week is all related to each other. You have the surface currents that are controlled by the first winds, which is the Coriolis effect. You get the heating of the atmosphere from the ocean itself. You get the heating of the ocean from the sun. We have all this kind of weird stuff that's going on. And Coriolis is sort of a predecessor for winds, which is what we're going to do tomorrow. And then winds and tides. Yes, I know tides are primarily moon and sun, but still all of this goes together. So in the Northern Hemisphere, if you are the observer, okay, and you throw something, it's going to put it in slow-mo so that you can actually see the curvature. Which way is it going to go? To the right or the left in the Northern Hemisphere? You have to think about which way the Earth rotates. Get it in your head. If you throw something and it has enough hang time where you can see the curvature, which way is it going to bend? To the right or the left? To the right. In the Southern Hemisphere, however, as long as you're throwing it in the same relationship to the northern, it's going to be looking like it goes to the left. So I have a few images. You know what? Let me fix that one that makes the Earth look like an egg. There's a weird picture in here. Let me fix it. See if I can make it bigger. Maybe this way. It's a little less egg-like. It's pretty bad. There we go. That's better. I should have done that in between classes and I didn't do it. All right. So we are going to talk about the Coriolis effect. There are a couple major differences between the ocean and the atmosphere. Like some of them are blaringly obvious, but you have side boundaries for the ocean. Eventually it's going to reach a shore and it's not going to go any further than what is sea level. And the atmosphere doesn't have those kinds of boundaries. It's a gas and it's going to fill this wonderful bubble that's within our magnetosphere. And now we're going to specifically talk about the troposphere though, because the stuff above that doesn't have wind, doesn't have weather, doesn't have any of the stuff that affects the hydrosphere. Let's see, who is this? Let me mark these guys up here. And this is actually a 12-day long unit. We're doing the first 5 this week, and then we'll do the rest of them. Well, I told somebody they could come in, and they didn't come in. That was weird. Okay, they'll come back. As far as the ocean is concerned, you can't really squeeze it down. You can squeeze down a gas really easily because it's compressible. And yes, technically water has a little bit of give, but in general, you're not going to squeeze the ocean into any smaller than it is already. The ocean has a top, the hydrosphere, yes, I know there's waves and stuff, okay, but in general, it's sea level, but the atmosphere does not. Now it pitters out between the troposphere and the stratosphere and the mesosphere and then eventually the thermosphere, but it's not like the ocean. It doesn't have these definitive boundaries because gases don't have a definite shape or a definite volume. We fill their container. And all of that wonderful stuff in chemistry right now. Just so happens that water is coinciding between both of my classes right now, which is weird. Your atmosphere is driven by thermal currents coming off of the ocean's surface. The ocean is, the surface currents are driven by responding to the air currents that are above them, specifically the Coriolis effect. That's what makes them work. And I have a bunch of different images. I can't remember what I put on your canvas and what I didn't. Oh, I haven't had a chance to make the retest yet. I've had people sending me messages and asking for it. I'm hoping I can do it today. When I get it done, I'll send out a thing. Let's see if it's the same person. So Jaron and Parker. Y'all ready? Sorry. Okay. Diabatic heating, all that means is it's primarily done by solar radiation. You have, yes, I know the oceans do get some heating from the sun. I understand that, but there's a much more aggressive change in heating with a gas than there is a liquid because there's fewer particles that have to be heated because it's in the gaseous state where they're spread out. Obviously, the air that you breathe shouldn't have a salt content in it. The water that evaporates into the atmosphere leaves the salt behind. The salt stays in the oceans or the seas, whatever. The atmosphere does get a lot of moisture. I know y'all hate that word, but I don't care. Now the ocean is way more dense. I mean, obviously a liquid is more dense than a gas. But of all of the oceans, if you could just take the top 8 feet, 2.5 meters, that's all of the moisture in the air. The rest of the ocean, like that's how much more liquid water is in the ocean than there are suspended liquid droplets in the vapor state. I'm not going to go over calculating heat capacity and all that good stuff. I'm actually building your CBA, and I keep coming across all the math I should be teaching you guys, and I'm not. So I'm not going to put them in there. Mm-hmm. Yes. Yes or no? Okay, so diabatic heating just means it's heating that's driven by solar radiation, is what it translates into. And like I said, technically they both do. It's just the particles are closer together, so it takes a lot more energy to heat them. Whereas in air, they're a lot further apart, and it doesn't take anywhere near the amount of infrared radiation or solar radiation to heat those particles. Which is why we have wind, which we're going to focus on tomorrow, but we're going to start talking about it today. We have to, because the Coriolis effect is tied into our wind currents. How do things move? We're bringing a lot of stuff. I believe it's from the second 6 weeks in today. High and low pressures, the way winds flow. Ready. So uneven heating. It could be forested areas versus desert areas. Like certain areas are going to heat up faster than others. The easiest analogy that I'm going to have is for those of you who have been to the beach. I'll get to that in a second. But you're going to have areas that warm faster, which are less dense, which are low pressures. Then you have areas that are going to cool slower. They're cooler. They're more dense. And those are high pressures. Who's this one? That's Huey. Okay. Okay, now I lost my place. Let's see. Now air goes from high pressure to low pressure. It goes from high concentration to low concentration. High energy to low energy. Same thing. It goes from more concentrated, which is high pressure, more air per unit volume because it's denser, to areas of lower pressure. When we take a look at winds tomorrow, we have these things called Hadley cells, and Hadley cells happen about every 30 degrees latitude. So you've got one going both north and south, between the equator and 30, between 30 and 60, and then between 60 and 90. And each one of these sections, they have names for their winds, but that's really tomorrow's topic. But in general, they're called pressure belts. We will learn their names tomorrow. Go through all of this. I should have more than enough time to tell people what they're missing. Like I said, we'll get, and there's a difference between global air and local air. Global, you don't, unless you go up in a plane, you're not going to experience the global winds. They don't normally come down to where we are. What you think of as wind is local. It has to do, I'll show you a picture of this on here. Like on the, gosh darn it. Okay, so it has to do, it's an air current and it's circular in shape where the warm air is going to want to rise, and once it cools, it's going to come back down, and it's just it's what it's called. It's just a convection. It's the way that heat is moved in a fluid, whether it be a liquid or a gas, where the warm is going to want to rise, it's going to cool, it's going to fall back down. It just so happens to do it every 30 degrees latitude. We have these circular patterns, which, like I said, we'll get more into Hadley cells tomorrow. I'm sure there's different types of them, but I didn't go that far into it much. Okay, so if it's the wind that you feel, that's going parallel to the ground. Yes, I know we've got hills and mountains and valleys, but it's the stuff that you can feel. Like when I was trying to work out yesterday, I was going full speed and I got hit with a big wind blast and it stopped me and I was angry. There's nothing I can do. So it did. It got breezy yesterday. If it's going up and down, that's a current. Okay? When you think of the x-axis, that's what we call wind. Hey, I really should have pulled this map back up from the second 6 weeks. We've got different types of air masses. Okay, towards the North Pole, we've got like the polar continental, and we've got polar oceanics, okay, and those were all pointing down. Okay, so the air actually goes from high pressure, the cold, towards low pressure, the warm, which is the equator. It's just, I'm going to bring that map back up yet tomorrow, and you'll recognize it. This has been, oh, I'm pretty sure there's one more on here. There is. So we mentioned this yesterday. It's warmest at the equator. It's coldest at the poles. They go from high to low, from cold to warm. So that's why the air is pulled from both of the poles towards the equator. But because the Earth is spinning, it doesn't do it in a straight line. It curves, which is the Coriolis. And it does so because I keep forgetting, like, I understand the physics, you guys probably don't. So like with centripetal acceleration, like if I take a ball on a string and I start wailing around my head and all of a sudden I let it go, it's going to go in a straight line at the direction that I let it go. It's not going to continue to go in a circle. It's perpendicular to the actual motion. It's tangential. And that's basically what happens with this. It doesn't go in a straight line because of the spinning of the Earth. It does so at a right angle to the motion. You probably don't understand half the words I just said, but that's what's happening. I will show you one physics equation. We will not have to use it. In fact, is it on the next slide? No, it's not for a while. Don't let the math scare you. We won't do it. That's going to change in years to come, but not for this year. Okay, so does the picture one? No. This, now, if the planet was a cylinder and not a sphere, then the winds would just go in a straight line. We wouldn't have any of these curves. But because the Earth is a sphere and the equator actually has more distance to travel per one rotation than it does as the pole, that's what causes this circular motion to happen. I don't know the exact difference in like miles or kilometers. I have to look it up. I just know that the Earth is fatter at the equator, and then it's like less distance to travel towards the poles per rotation of the planet. That's what makes it bend. And like I said, if you go off to advanced physics and they teach you actually how to calculate this, it's pretty nuts. And I didn't want to scare you, so I only put up one. Let me check that real quick one more time. Who else is online? Huey, Parker, Jace. Sheila.
Hey, Mr.
Sheila.
Q, we got out of baseball really late today, and I live like 15 minutes away, so that's why I was late.
That's okay. I got you. I'm checking constantly, so
Sounds good. I was just
it
letting you
so
know.
happens to be what I'm doing right now. Joe Holmes not here. Nathan Harper. Principal. Frontier. Josh Gunner. Okay, that. Okay. Fixed it. Okay, this picture, I sort of fixed it because the top one's still a little egg shaped compared to the bottom one. Oh well. I can't remember. I know I didn't blue much out, so that must be most of this that it's asking on your thing. You've got things going from higher pressure to lower pressure. We've got the spinning of the actual Earth in the northern hemisphere. So like you're standing here, and so like you're like throwing away. But if you could sort of slow it down, like to make it do a lot more time within. Anyways, if you could actually see it move with the curvature of the Earth, it would be deflected to the right. Even if you were facing towards the South Pole or the equator, if you throw it, it's going to deflect to the right. On the south, if you're pointing, or well, the southern hemisphere, if you're pointing towards the equator, it's going to bend to the left. They bend opposite directions. And it's, like I said, if you flush, now this is different, but if you flush the toilet in the northern hemisphere, it's going to go clockwise. If you flush it in the southern hemisphere, it's going to go counterclockwise. No. It has to do with the way that the Earth is spinning. So, now I've never actually tested that out, honestly.
I have.
Have you? Yeah, I mean, I've just never been, I don't think I've ever been south of the equator. So, I know it's weird. It's just, but it has to do with the way that the Earth is spinning. All kinds of weird stuff that happens on this planet. I don't need to change you off of that, so just do that. Oh! All right. So once again, winds are caused by uneven heating of the Earth. I guarantee you this will be in your CBA in some way, shape, or form because I'm just now starting to build it. You do need to know that air goes from high pressure to low pressure. So that means it's going to blow away from highs and it's going to go towards lows. So it's away from the colder front and then towards the warmer front. I think that's like on your CBA twice. It's just, I'm not going to tell you exactly how the question's worded. Now, there are two types of winds, the type that you do not come in contact with unless it's like airplane related, okay, because they're high off the ground, or the ones that you are used to, our weather system, the winds, the storms. The planetary is just sort of like, well, it depends on what kind of clouds they are, but what you think of as the big poopy clouds, it's above those. And like I said, we're going to go much more in depth with this tomorrow. The only winds that we talked about was like a northerly wind blows from the north and then into the south. Like that was really all we did with winds. We need to go over mountain breezes, valley breezes, ocean breezes, which you may already know. For those of you who've been to the beach, if you're on the beach during the day and you're facing the ocean, which way is the wind blowing? Into your face. Now, let's say you go visit the beach at night. You're not doing bad things. You're staring at the ocean and it's at night. Which way does the wind blow? Out to sea. It has to do with specific heat. The land actually heats up and cools down faster than the ocean does. So during the day, the land is hotter. Okay, that's high. The ocean is cooler. That is low. You're going to have it go into your face. And then vice versa. At night, it cools off faster. So it's a cold front. It's a high pressure. You've got your warmer air over the ocean, which is less dense, which is a lower pressure, and so it goes the other direction. Best place to fly a kite is on the beach during the day, because there's plenty of wind. This is the only formula I'm even going to remotely try to explain to you. Because of tangential velocity, the motion is perpendicular to the direction of motion. Once again, I'm speaking very, very physics because that's what this is. Like we said, it's to the right in the northern, to the left in the southern. Now this particular acceleration is 2 times the rotational constant of Earth, which I do not remember off the top of my head, but that's what the omega is, times the velocity that's being traveled of whatever object is moving, times the sine of the whatever the latitude is in degrees. You are not going to have to use this. It's just I had people asking me like what formulas were there. Basically, as you go further away from the equator, your acceleration is going to be larger. At the equator, latitude is 0. Anything times 0 is 0. So at the equator, you don't see curvature if you throw something and have it move with the rotation of the Earth because you're 0. So it's 0. That's how that particular equation works. Trust me, if you go ahead and look up Coriolis acceleration equations and Coriolis force equations and have fun with it, because yeah. Now, when air moves with this one, not the equator, because it's, yeah. When we did isobar maps, you had these lines that would connect, and those had to do with different pressures. Your winds are going to follow along those lines. So these poor meteorologists that are trying to predict the future, they're taking a look at all of these things, including this. They're looking at, if you live towards the coast, they're looking at the stuff that's going on in the ocean, and they're trying to predict the future. Sometimes they're right, and a lot of times not so right.
What's the name of the symbol that's in the version?
It's an omega. It's a Greek.
No, I know that one. The other one.
Oh, that's for latitude. That's however many degrees you are in latitude, which is why at the equator, which is 0, this ends up being 0. But this is, I mean, it's not that difficult. It's just some of the other equations, they're a little nasty. There's letters in there that I've never noticed before, ever. A high pressure, when we're in the northern hemisphere, highs, so it's just been a while. There's a difference between a high and a low. Highs are going to go clockwise and they're going to push out like that. And then lows are going to go counterclockwise and they're going to push in. So this is like a hurricane. This is what, and then it has to go up, creates the eye wall, then it diverts out, makes a nice big bank of clouds. High pressures don't do that. Get the other one up here. Both of them do have a deflection to the right because they're in the northern hemisphere. If we were in the southern hemisphere, everything's reversed, but a low pressure still pulls in and a high pressure still pushes out. It's just the arrows are all reversed, but you're still in the northern hemisphere, so we still have a deflection to the right. Once again, southern hemisphere just invert everything. What is right is left, what is clockwise is counterclockwise. Yeah, I think it was on the last one. That just means that, yeah, if you have wind, okay, and we're at latitude, not equator, then your winds are going to follow along the isobars, the different pressures. It's just been a while since we've done that. We'll talk a little bit more about hurricanes here in a second. Yep, you ready? Okay, so like I said, they're both deflected to the right. The top one is a high pressure. High pressures go clockwise and push out away. The low pressures are going to go counterclockwise and they pull in. So if you do move somewhere on the coast, or if you're on vacation and there's a hurricane coming, if there's a high pressure sitting over top of you, as long as there's not another high pressure next to it, which was what happened with Hurricane Harvey and it was trapped, highs push away. So that hurricane most likely will be pushed away from your location. But if you have a low pressure on top of you and there's a hurricane coming, it's going to be sucked right towards your location because lows pull in. I had a major crash course with how these things work when I moved down to the Beaumont area. I'm so glad I'm not there anymore. So this nice red band or pink band, this is where the warmest water is because that's where the equator is. That's where our tropical storms want to form. They need warm water for our area, at least 79 degrees for the Gulf. You need to not have dry air. It's making a giant rainstorm. And it's going to be affected by the Coriolis effect. This is what helps spin these things. And then the names of the different storms. So obviously we call them hurricanes here. I'm not sure specifically where they call them cyclones, but typhoons, that's more of the Asian area. It's the same thing as a hurricane. It's just a different name for it, just a localized term for it. We've got 3 more total. We'll be done
Can I go to the
probably.
restroom?
Yeah, just like I said, A-Hall is always going to be your best bet. We got an email yesterday saying that we are not to unlock the multi-stall bathrooms if they are locked for students, period, end of story, that there are single person bathrooms somewhere on campus that you're supposed to use. Yet the women's is open right now. I don't know. They may just not realize that it's unlocked over here. I'm not going to complain because I don't want to have to run to A-Hall between classes. All right. Just as a refresher, category 1 start at 74 miles per hour. It goes up to a category 5. I'm not going to go through we've already done this. Now we got something insane, like almost 30 storms last year around in the Gulf, and then a few of them off of the west that went across Mexico and then into us. But across the world, we normally have around 100 of them. I don't know what the actual number was last season. I should have looked that up, and I didn't do it. Yeah, that didn't go good. There's tons of hackberry in the air. I'm allergic to it, big time. Now, we start hurricane season back up in our country June the 1st. Last season was unbelievably active. Poor Louisiana got slammed like 5 times. Now, in a hurricane, for those of you who don't remember, or maybe if you do end up moving anywhere off the east coast of the Gulf, in a hurricane, because they're spinning like this, I should have left it up there, so we're going to go in. Because they're going like this. This is your low. If this is the coast, I really need to invest in some different colored. Oh, this is like, so we got ocean this way. This side actually sucks the water up, and this side actually pushes the water back out to sea. So if you do have to deal with a hurricane, this is actually the worst side to be on because this is the storm surge side. This is the, as far as debris, the cleaner side if you're off the ocean. But for water, this is called the dirty side. On this side, as far as storm surge is concerned, is the dry side. But when it comes to debris, this is actually the dirty side of the storm. So I would actually rather deal with this side. I would rather not deal with it, period. But I'd rather deal with this side than this side. Just because of you cannot get away from the storm surge. Hopefully you never have to deal with one of those because they're not fun at all. All right, so I do not know how they measured carbon dioxide levels 200 years ago because they didn't have the technology to do it. But according to modern consensus, our carbon dioxide emissions because of the Industrial Revolution has gone up 30%.
The carbon dioxide in the ice in the toilet.
Do what now?
I thought they measured the carbon dioxide emission.
They probably did. They probably did, but I know they tend to use oxygen more than anything. I'd have to go back and look at it. But this is the time period of the beginning of the Industrial Revolution where we started making things. Okay, and obviously it was more coal. It was a lot dirtier back then before we learned that we were not doing the best of things. We'll get more into human pollution next 6 weeks. Now in actual like temperature recording, like actually understanding this, it was the exact temperature. It's gone up worldwide, okay, so not just regionally, 1.1 degrees Fahrenheit. You're like, big whoop, that's nothing. But when it only takes that extra degree, specifically where the hurricanes form, it does make a difference. And I just said this and didn't realize that was the next bullet. Now, it needs to be 79 degrees to start spawning, not tornadoes, hurricanes in the Gulf, well, anywhere along the hurricane belt, off of Africa. And it comes this way. Sometimes they hook up, sometimes they go down, sometimes they go into the Gulf of Mexico. One more. Like I said, a typhoon is the same thing as a hurricane. We got one more. And we'll do a lot more of like how fossil fuels are created and what the pitfalls are, renewable versus non-renewable energy. All that stuff is like right towards the end of the year. That's fun. We've talked about this off and on for quite some time, especially when we were doing the evolution. Can you go back one more? That it doesn't take much of a change, you got it, in the sea level to cause some type of an effect. If you alter the currents of our ocean, you're going to have some type of side effect. It could be warming or cooling. We now affectionately call it climate change. All you have to do in the case of the ice ages, we created that land bridge and we separated the Atlantic and the Pacific Ocean. That had dire consequences. If you alter the major streams or gyres, if you alter that conveyor belt that I showed you guys at the end of last year, that's going to totally mess stuff up. Now, what else happens? So you can have insane monsoons, more towards India is where those happen. Africa is still exhibiting a horrible drought, like the Ethiopia type areas. It's been that way since, oh my gosh, since I can remember. It's just been horrible. Now, when you have flooding and it gets into our sewer systems, which are now backlogged, here comes diphtheria. What are all the other nasty ones that make you poop until you're dead? Dysentery. Dysentery would come back. You don't want to contact any of that, but if you're unfortunately wading through flooded waters that have been contaminated, then you have a higher chance to get it. We're going to have longer summers that are hotter. You may have animals that have to move because their food sources have now changed. Plants may dry out. They may take over other areas that become more habitable for them. And then the last thing on here, we know that the northern cap, now they'll both melt. The northern cap does so at a much faster rate. When it comes time to refreeze, then the southern Antarctic cap is going to grow much larger in relationship to the northern cap. So I know, they keep saying, oh, global warming, the ice caps are all going to melt, we're all going to die. And it's not meant as an aggressive as an event as they said it was going to be. What's his name? Who's the new EPA director? What's his name? John Kerry? He said originally that Manhattan would be underwater by 2006, something like that. That didn't happen. So, I mean, I'm not saying that humans don't have an effect on the environment, but it has sort of been exaggerated, and it hasn't always been based on actual science. Let me stop the recording so I can get